Hello guys, thank you for coming to Olewave channel. We're a channel that reads the latest archived works, including the published works. And this is the last day of 2022. So we're gonna be continue reading the famous paper Clip by OpenAI. In the previous video, we have finished the introduction, the algorithm, which is the section 2 approach. And in this section, we're going to be reading the third section, which takes many pages and is very important in this paper. It shows how the authors analyzed the findings of their clip-based algorithm. So for those of you who have not seen the algorithm or approach part of this paper, please spend your time watching the last video I uploaded on the YouTube. So if you're in the Olewave channel, just a search clip approach or algorithm, you will find the video. Okay, so before I start, I want to tell you why I think the experimental section of this paper is worthwhile reading. Definitely, if you finish reading the experimental section, you will find, okay, those are all common sense to me. But it shows the authors, how do they come up with the idea of a clip? And why do they choose a specific model architecture and the way they leverage the models, especially in the zero-shot transfer learning. And you may also be able to know the direction of the future works of the authors, and which is very important, which is more important that I want to try to inspire you. Of course, I got inspired by the authors, that for those of you who are doing PhD research, this might be important for you to come up with your own thoughts, idea, because this also shows how to do analysis on the data or the experimental results they have. In one word, in one sentence, so research is not about getting a number, say ImageNet 85%, 95% accuracy. It's all about findings. How do you come up with new thoughts based on analyzing the existing data you have? Okay. Let's talk too much. Let's directly move on to experimental section, which is the third section of this work. First of all, they talk about zero-shot transfer. I assume that most of you who are familiar with zero-shot transfer, suppose you're a computer vision guy, I would assume that you're fairly familiar with this. But for speech folks, I think, and also NLP guys, you will know what the zero-shot transfer means, of course, because I think nowadays, because everybody is using the large language model or the BERT model, basically the scenario you have is basically all zero-shot transfer. Okay, lots of scenarios. But for speech guys, we do not use zero-shot transfer a lot because it does not work yet. Which means suppose you train a model on LibreSpeech and you use that for telephony, dictation. If you do not have any data, so the going from one domain to another domain, your model would pretty much fail. Okay. But zero-shot transfer means that you do not have a data set for you to fine tune, and you cannot have a validation set. So basically you just have a test set. Or how do you say that zero shot? Zero shot means that there's nothing in the training set, but you do have one shot in the testing, okay? Inference, you just have one chance. Tell me what bird this is, and what word I said, or what do you think this means by looking at just the text, okay? After talk about the ZST, we now try to see if my and works ZST. Yeah, I think the author had a very nice text. It just means generalization to unseen data set is very important with the model to have the capability of zero-shot transfer. You can think about this. If the model can, or the pre-trained model can only work on one specific data set, say ImageNet, it lost the capability of generalizability. So for a new data set, for example, satellite image or car object recognition, it won't work at all. So what's the point of having this pre-trained model in this zero-shot transfer learning? Doesn't make sense, right? Okay. So it involves a very hot topic in not only the computer vision, but also NLP and the speech, which is representation learning. It measures the task learning capability of machine learning system. Yeah, same thing. One thing is interesting is you can see that I read this. Zero transfer is more an evaluation of clip's robustness to distribution shift, the domain generalization, rather than task generalization. What does that mean? I think the section 3.3 would talk more, but definitely you will see more about distribution, the keywords here. What they meant is for image classification, even you do not shift your domain, your distribution could also shift, because you all know ImageNet. But the computer vision researchers, they alternate the organization ways of the ImageNet, so they come up with the variations of the ImageNet. So the task is still the same. There's just tons of classes. You have to tell which class this object is. The domain probably has not been changed, because the altered data set, altered version of ImageNet still use the class labels that the original ImageNet uses. So it's more about shifting the distribution of certain classes to another one. So that's what the distribution shift means. And domain generalization is easy to understand. Suppose you train a model on ImageNet, and then you apply the model using some noisy student training or transfer learning technique to see if the model works on satellite image classification, okay, or segmentation. That's more like domain segmentation. Task generalization, I think for computer vision, correct me if I'm wrong, because I'm not a computer vision researcher. for computer vision, I do not think there's an. If you talk about image classification, that's not task. Image classification is a task, right? They all doing the image tasks. But if you're doing the going from classification to segmentation, that means the class task has changed. Okay, that makes sense. But if you're going from ImageNet to satellite image classification, the task has not changed. It's still classification. It's not going from classification to segmentation. Okay, I think they tried to compare their zero-shot transfer learning with a method which was proposed in 2017. It's called Visual Engram. I mean, you will see that I explain the Visual Engram in the algorithm section number 2. It's basically about the difference of the visual engram to clip is that this algorithm trains on engrams. So the target is engram, okay, word engrams. But the clip is the target is, what do you call that? I think they have a special I kind of forgot what they meant. Oh, they train on natural language supervision. Okay, natural language supervision, but this is trained on Engram. Okay. It's more like a word based. This is more like a language meaning based or semantic based. But definitely, they can have lots of engrams. Suppose this is ImageNet, right? And this method, I think, it's fairly straightforward, right? You can imagine that this method for zero-shot learning, basically what it does is it's still using the same architecture the clip uses, I think. If you see, I explained the zero-shot prediction here. But you can imagine that for visual engram, there will be no text encoder, correct? There will be engram, all the engrams here, and try to compare it with the image encoder to see which one gives the highest probability. Very straightforward. The only difference between them, the clip and the visual engram, is the visual engram. They just say the things need to be compared here are engram things, right? But the clip, they come with the embedding coming out from the text encoder. It's no longer words. It's some meanings from the text or some summaries of the text. Okay. I have to come back to here. Okay. Yeah, here they talk about exactly what they do in the clip zero-shot transfer. It's actually starting from here. To perform zero-shot classification, so for each data set, I think I would. I think I explained this in the approach part. I think you will be able to know this, but to make this as a complete, I would just quickly go over this again. So there will be n classes, and for each zero-shot classification sample, for each sample, here, image sample, to be ZeroShot classified. They first pass this to an image encoder, got embedding right here, see, I1. Then they pass the n different words, and they combine this with a certain type of prompts. We will cover the prompts later on. It shouldn't be definitely you can just input a single word into the text encoder, but the result won't be good. So it will be better if you engineering the prompts in a proper way. So they mentioned that the better you organize the prompt, the better result you may get. Okay, but for the after text encoder, you got n different text embeddings. Then you can compare the cosine similarity of the image embedding with n different text embeddings, and you pick up the and I think they also, so then they pick up the highest pair that has the highest cosine value, or after softmax you got the highest probability, things like this. And then you check the ID of this, and you see, okay, this is dog, right? Okay, finally the result is dog. That's the classification result. I think it's straightforward. I think the author are very nice. They remind you, don't forget this is multinomial logistic regression classifier. This means, think about this. I think the classification would be accepting a tensor with the size of a b, which is batch size, and u is the number of word pieces in one description. Remember, a photo of something, right? That might be, in this case, a photo of something. So that's 4 words. Definitely, you decompose into word pieces, and then you have to add the start of sentence, end of sentence, things like this. The size of the length of your text input. Definitely, in the end, you will have the class. Okay, this is 10. C is a class. So this is why they're talking about this is a multinomial logistic regression classifier. And the B, sorry, think you need to be batch size. Usually the batch size during inference should be 1. Okay, so you can see this is U times C. It's not just the C, because the U here, the number of units in the sentence, and then this become a multinomial logistic regression. Otherwise, it will be a by. Oh, I'm sorry. It's against the binomial. Binomial means there's only 2 classes, but there are multiple classes, more than 2. Okay. Okay. I think there is a gold sentence you have to read. Every step of clip pre-training can be viewed as optimizing the performance of a randomly created proxy to a computer vision dataset which contains 1 example per class and has 32,768 total classes defined via natural language description. Oh, this is a sentence so long. It took me some time to understand it. So you can pause the video and think about what they meant by this and come back. Okay, after you pause the video, let's try to explain this. First of all, this is not in inference. or zero shot inference. This is talk about training. Or pre-training. And you may ask, what does this mean? Remember this number? This is their batch size. You can go back to the approach to check by yourself. This is the batch size. They do have a very large batch size. Remember, in each batch, they have 32,768 image and text pair. Okay, image text pair. And then let's go back to this part. Okay, this is 3270. With this one, so you can imagine that, okay, the class number should be, or the n would be, am I right? This is also right. So this is why you understand, okay, the pairs the number of pair is 32k, and the class number is also 32k. So each class has just one sample. And what's the training target for calculating the loss? The target is, so target is this: T1, T2, T3, Tn. So it's no longer like the visual engrams or class labels. There's no exact 0, 1, 1, 0 thing. This is a vector. Each T1 is a vector, okay? And it's no longer cross-entropy loss. So not cross-entropy loss. So this is a contrastive loss, okay? Contrast. Or you can call that cosine similarity. It's up to you. Let's see, let's go back to this. So this is why they're saying this. The randomly created proxy to a computer vision dataset, which contains one example per class and has 32,000 total classes defined via natural language description. This means the output of text encoder. Okay. And the proxy also means this, I think. So it will be no longer the labels, but the embeddings to be the learning target. Okay. Okay, now, yeah, they're talking about cache. This is about engineering implementation details. If you're doing inference, this is they jump to inference now. They don't have to calculate the text encoder every time, right? Just using the cache. All right, let's move on to the comparison to visual engrams. The authors admitted that this may not be a fair comparison because the dataset is 10 times larger. The computational power is 100 times more per prediction. Okay, because why? Because the dude zero shot. Okay, there's lots of computational power involved, and the training time is even more. Okay, a model size is larger, of course, but they do get on ImageNet or ZeroShot they get way better results or acceptable result compared to Vision Engram. And on the other two data set, they get some way better result than them. Yeah. And then they talk about prompt engineering. I think this is a very ad hoc thing, but the authors would like to mention this. Remember, lately people play with the stability fusion, the tools that you can use for automatically leverage the AI to draw animation pictures or cartoons for you. But say you want to say Albert Einstein riding on a unicorn, but think the picture generated would be different if you say Albert Einstein riding a furious white horse. Might be the same thing, right? But to my understanding, but the AI would draw way different pictures sometimes because your prompt has changed. So this is why during zero-shot transfer learning, the author found that okay, getting a better prompt is important because they say because most of the time during pre-training, they're not training just one single word, right? If you see this, let's go back to the picture. What they talk about is here, the pair. Most of the time, this text prompt is not just a single word. So this is why also common sense, I think, doing the zero-shot transfer, you should also provide some prompt. Okay, this is like this. This is a prompt, one example of prompt. Okay, and this could slightly improve the accuracy on the ImageNet. Because of why? The reason I think they thought having the prompt engineering would be helping was because polysemy. Poly means multiple. Semi, so this is a suffix or prefix of a semantics or SEM. Is the NLP meaning, okay? Multiple meaning of the same word, okay? So suppose you just offer one word to the zero shot thing, okay? Then you would say, okay, this is fairly difficult for the model to know what you're talking about because it lacks of a context. I'll give you some example, okay? Boxer. Boxer is a breed of dog, right? But if there's no context, people may think, okay, this is an athlete. Okay. Yeah, they show some examples of prompts. For example, suppose you know your domain. Yeah. Suppose you know your domain. For example, you just don't pet. Okay, pet is probably your domain, and also satellite is your domain. Providing this can improve the classification accuracy of your zero-shot transfer. And also they do ensembling. So ensembling they mean they can average or gather the results of the multiple zero-shot classifiers. And that's easy to understand, okay? Improvement, additional 3.5%. If you add the voice prompt engineering together, you will get another 5% improvement. Analysis of ZeroShot Clip performance. Next subsection. This is what they show in figure number 5. They come up with some. Their conclusion is that the ZeroShot Clip is quite weak on several specialized, complex, or abstract tasks such as satellite image classification, no tumor detection, whatever. It's basically these things. Yeah, but the clip model did really well on the common things or daily activity related stuff. For example, cars, food, things like this. Does pretty well. Why? They're trying to analyze why this is the case. I think they've come up with some explanation. First, they say Clip ZeroShot classifier is generated via natural language, which allows for visual concept to be directly specified. So this is why you see the satellite or the tumor cases, they're more like a contextless example, okay? This is the drawback that many different hypotheses can be consistent with the data. Many different hypotheses can be consistent with the data because the context is gone. You have to, the information for you to remove the confusability is not there. Okay, and this is why in the ZeroShot classifier it's very difficult because you do not have this information available. That's the explanation, especially in this one-shot case. Oh, I think I jumped to the figure number 6. But let me finish that figure number 5 first. Yeah, I think they just talk about this is the take-home message of figure 5. So what I just talked about was figure number 6. They talk about few-shot linear probes. What does this mean? So this means, so suppose you got a clip model. Clip model takes image, right? They come up with a visual embedding. And then you put on a, what do you call that, linear classifier on top of the clip model. And then, so whatever, how many shots you have, how many training samples you have, you can have 1, 2, 4, 8, or 16. And then you use these samples to learn the classification hyperplane of this linear classifier. I know it's difficult if you just have one sample, right? This is the reason why the result is very bad when you're just giving 1 or 2 samples, but it's getting much better when you have 16 samples or more. And then they're talking about why the one-shot learning. or few shot learning could fail was because it lacks the capability of using the context, while the clip zero shot classifier can benefit from the natural language. So this allows the visual concept to be directly specified, because definitely you can say, okay, this is a photo of a pet. So when the pet is got input into the network, it tries to correlate the pet with the certain image it has seen before. So it how to say that, it gets the meaning of the current scenario and help the model to better understand the input and get a better result compared to the one shot or few shot cases, which cannot leverage the natural language part or visual concept part. Okay. I hope you're following with me. So for those of you who are attending the Zoom meeting, you can come back to the Olewave channel, and I will upload the full recordings, and so you can finish the rest part. Okay. And I wish you Happy New Year. Bye, guys. Yeah, they are talking about some ways to alleviate the few shot learning. So they can say you can use this clip zero shot classifier as a prior. Definitely, this is like an ensemble model to me, or multitask learning. It just combine the two models together. Definitely would be in the middle of these two, but should be better than the original clip, right? This is trivial, I think. Yeah, they're doing some comparison between the ZeroShot Clip versus the performance of the best performing 16-shot classifier. I think, well, this is what they're talking about. They're saying this clip is almost as good as, or roughly the same as, BeatM. So other people's method. And this is, correct me if I'm wrong. I think BeatM is some other model. Oh, this is not an unsupervised training model. This is trained on a ImageNet 21K. It's a supervised model. Okay. And then they use this for another task, for another domain. So it's like a zero shot of this model in this case. But these models are not supposed to be working well when they train on ImageNet and the zero shot on another domain. Okay. I think there's not much information. We're gonna move on to the figure 7. Yeah, I think talking about the performance, they also talk about how their proposed method or zero shot clip versus the fully supervised classifier. Okay. For most of the data sets, I think they compare. Oh, they're talking about figure set. Let's first go to figure 8. Okay. How do you understand this figure? Okay. Take the country 211 for example. Okay. The The linear probe clip performance means that you use the clip model and you train you use a full data set of training data set or country 211, you fine tune the linear classifier. Okay, remember this model I talked about? So you use all the data sets, training set in the country 211 to update the parameters in this linear classifier. Okay, after you're done, then you run the inference on the development set and test set. Okay. And then you got about 47% accuracy. And then you can see here, if you're just doing the ZeroShot clip, you're gonna get about 35%. But this is 47%. So this is a gap. Or how do you say that? Or this might be theoretical upper bound when using ZeroShot clip versus clip plus the full supervised fine-tune model. Okay, and you can see that. I think this is a linear fit of those data points, right? You can see sometimes it can do really well for this. For example, I know CFAR. Okay, you all know CFAR. CFAR, you know, is very close to the x equals to y line, right? That means that for this one, the drop from the full supervised to zero shot is very minimal. But for other data sets, you can get about this. They talk about this. Most of the time, you underperform the fully supervised data set by 10% to 25%. They say there's a pretty much plenty headroom for improving the clip's task learning and the zero-shot transfer capabilities. I agree, but how to do this is a question. Yeah, they talk about when the gap between when the gap is small, this means the clip is more effective, where its underlying representation are also high quality. Okay, that's the takeaway. Yeah, I think this is common sense. I think you got it. And they talk about figure 7. I think figure 7 is easy to understand. They're talking about, suppose during the few shots learning, you can have many shots in the training set. How many shots do you need to reach the performance of a zero shot training? So you can see that except the Euro satellite and Flower 102, most time you need more shots, more than one shots to achieve the results of zero shot, which means the zero shot model is fairly generalized, works very well. And they're saying that, remember this, this means this means that this is due to 20% of data set where supervisor classifier require many labeled examples per class in order to match performance. Okay, very clear. I think they have presented lots of data, lots of experimental results. So sometimes, to me, what's the purpose of serving these experiment is a question to me. But in another sense, I think it's useful because different researchers or different people can look into certain or one specific experiment they are interested to see whether this is helpful to them, because not everybody can have the capability of training this super large clip model, let alone running the zero shot experiments using this trained model. So getting as many experiments on this archived works make the other researchers to be easily using their work as a reference to certain results or their own research directions. Suppose they do not have the computational resource or data resource. I think this is a nice thing. Okay, then we move on to figure 9. This is easy to understand. They're saying that again, this is only ZeroShot Clip model, and you can see the arrow goes down when the model size went up, and this has a perfect log linear. This is a log, right? Log scale. This is a linear scale. So this is like a log linear relationship between the error and the model size. I think this is common sense. Representation learning. This is study the representation learning capability of a model. This is the definition of representation learning. I think there are two good things as mentioned by the authors. The first good things when you have to use a linear classifier. Yeah, because on top of the pre-trained model. Fire. Gee. I think I drank too much wine. Classifier. Okay. Other than using a nonlinear classifier. First, because it's not flexible. So when something failed, you cannot blame the linear classifier. It's more about, okay, you blame the failure of your clip model or your pre-trained model. Okay. The second thing is that this is the first thing, you can provide clear feedback of your model. And also it highlights the failure. Okay. First of all, it highlight the failure of your model. The second thing is that you can provide clear feedback. Because suppose you use a nonlinear classifier. When something failed, you cannot tell whether it's the failure of your nonlinear stuff or the model or the pre-trained model. Some people may not be very happy because they want to see what's the best number the model can get by using a nonlinear classifier. But definitely this is not the point of these authors was trying to make. Okay. And also you may have known that they have to study 66 different model on 27 different data sets. That means they have to fine-tune almost 2,000 different evaluations. This might be too much. So the linear classifier does not need a lot of hyperparameter tuning. It's easy to tune, right? Probably you don't need much work to do this. See this? Compared to nonlinear classifier. Yeah, it's a practical choice. Now let's see, to study the representation learning, they present the figure 10. Yeah, this figure is not easy to understand, but let me see if I can explain this clearly. First of all, this completes 12 data sets are, in my understanding, the variations of ImageNet. And these 27 data sets are more general. So it does not have to be in an image data set, or it could be satellite, for example. I don't know whether that's true or not. It can be satellite image, the medical image, tumor stuff, things, etc. like this. Oh, before we hop on to figure 10, oh yeah, on the figure 10, you might be able to see one important findings in this work, which is the vision transformer works way better than the convolutional based model or ResNet model. Why? You see, let me use a. This is the red line here is a VIT, and this is the ResNet. It's way better, you see. So given the same computational power, the accuracy can get higher, way better than this. See that this is a VIT, this is ResNet, okay? And on a general data set, the conclusion still holds. See? So you see the gap is big. So the conclusion is that, yeah, always use the VIT and not use the ResNet when you are training your own clip model. Okay. And they're saying that the model works better than the best model of other people uses, which is what model? This one. Use this one. You see the blue line here? It's called the efficient noisy student. I think EfficientNet is fairly easy to understand. They're trying to say I optimize the depth and width of the model at the same time. It's fairly standard method nowadays. But what does the noisy student mean? It means that, first of all, suppose they train a model on ImageNet, okay? ImageNet. And then they switch the task to satellite image classification. Okay. Then what they do is, suppose this one has a linear classifier of ImageNet. Sorry. Suppose originally they have a classifier, linear classifier, right? See this? This is a clip model, right? No, this is EfficientNet. Sorry, it's not ClipNet model. Let me use the EN means EfficientNet, okay? And when you try to go from this model to SST. Remember, this is a supervised train. Supervised. Noisy student training means that you do transfer learning. Usually, you train a new linear classifier, then you go there from there. Does that make sense to you? Yeah. But basically, you have during the transfer learning, all you have to do is you may need to have your own clip model, or you probably don't have to. So all you have to do is make sure the output of the linear classifier and the output of this linear classifier to be as close as possible using the, for example, KL divergence or L2 regularization, whatever you want to use, okay? That clear? Hope so, okay. Basically, the idea is the noisy student training is a transfer learning technique. It tries to replace the upper part of the model into another one by leveraging some KR divergence or L2 regularization technique, whatever. So definitely this works better than the original efficient net. Yeah, this one. You know why? Because this is zero shot learning, okay? You don't have any shots. So when you go from ImageNet to SST, if you don't do the noisy student training or transfer learning, and this model would be not fit for the satellite image classification task. In speech, we call that domain mismatch or whatever mismatch. But in image, they could call that distribution shift or domain shift, something like this. Okay. But remember, I think this is all this selection. Let me see whether, yeah, I think they implicitly regard this as a zero shot case, zero shot transfer learning case. Okay. All right. In the figure 10. Let me double check. I think they come up with a noisy transfer learning. Yeah, I just assume this is a zero shot transfer case. And they say, they also mentioned that, okay, the efficient net, when they transferred from ImageNet to another variation of when the task or the domain, shifted from ImageNet to a variation of ImageNet, you can see the performance drop, the gain of clip model versus the efficient net noisy student is less than the things shown in the right figure. For example, you can see the improvement is like this. Okay, you see, this is the blue line, this is the red line, this is a VIT, right? VIT. This is the efficient net noisy student. And then when you move on to more generalized data sets, then you can see that the proposed clip model at G-flops 100, you can see the improvement is this. Much larger than improvement over here. Because of why? Yeah. Because I think the author, they mentioned that as shown in the appendix, figure number 21, clip models learn a wider set of tasks that has previously been demonstrated in a single computer vision model trained on end-to-end from random initialization. Yeah. This one means the single model trained from end-to-end from random initialization. This means efficient net, for example. Efficient net model. So this is much better than the existing method people are using. Okay. Because how to see that? I think this is the purpose of this subsection, representation learning. They are just suggesting that the KIP model can generate a better representation of the raw data. So in the zero-shot scenario, it works better than using end-to-end trained model from another data set than do the transfer learning. So it's better than the previous technique. So all you have to do is to first do the self-supervised training, and then you do the zero-shot transfer. So that's better than doing the previous methods. And what they're suggesting is here. Remember the blue line I just talked about? So the more diverse your task is from the original data set you use to end-to-end train your supervised model, the larger gain you would obtain compared to transfer learning from a supervised trained model. This, okay? Make sense? Then we move on to figure 11. They're saying that yeah, I think figure 11 is interesting, but it's easy to understand. So still, they're trying to compare with the efficient net L2 noisy student transferred model, and this is their clip model. Still, what do you call that? Zero transfer learning scenario. And by the way, you can see that over the image net, okay, the clip model is worse. And because image net is, how do you say that? Is previously trained on image net, right? So this is getting better result. But the clip is trained on lots of data set in a supervised fashion. It does not just try to optimize on a specific data set. And it works very well on data sets like this, which are the distribution is different, way different than the ImageNet. Then you can see the clip model has the capability of learning a generalized representation, so it works well on the zero-shot transfer learning compared to the transfer learning based method. And this is mentioned like shown here in distribution performance. Yeah, in speech or speech recognition, we usually call, we do not have this in distribution terminology. We usually call speeches in domain. For example, the in domain could have different domain, could be reading, okay, reading books or audiobooks, okay, audiobooks. Or TED Talks, right? TED Talks. TED Talks is dictation. This is dictation domain. Dictation. Or you can have telephone conversation, okay? Telephone conversation. So these are different domains. But talking about distribution, I think for speech, we also may have something called in distribution. For instance, telephone signal is one distribution, right? But also if you're using the microphone array, it could be another distribution. Or you suppose you went into the subway and you talk to people, there's lots of noise. That's another distribution. I hope this help you understand what they mean by in distribution. Yeah, they're talking about for different distributions, they might be spurious, and the distribution might be very different from the other distribution. So model trained on this certain distribution wouldn't work on other ones under the zero shot scenario. I think this is very important because lots of time, I think probably 3 or 5 years ago, people are keen to improve the classification accuracy on the ImageNet. They say I got 85%. They got say I got 85.1. Say they got 86.1. This is slightly by slightly improvement, but to achieve the artificial intelligence or the capability of human being, it probably would be more important to make the image recognition or classification to be able to work on different distributions. For example, satellite image, tumor detection, object detection on the road, right? Other than just classifying the categories of the image objects. And they're talking about this is interesting. I would recommend you to read this paper, although I haven't read this one yet. They talk about natural distribution shifts. What these totally do? Okay, they grab the ImageNet. Okay, then they train some model on the ImageNet, and they call the variations of ImageNet 7 data sets or 7 alterations of the ImageNet. They call that on each set there is a natural distribution shift from the original ImageNet data. Okay. And these distribution shift is different than the synthetic distribution shift on some other data set. I mean, this is maybe 2 or 3 data sets. These sets are by scaling and twisting or doing some network synthesizing. It's different. The important thing is natural. They want to see the model can be generalized so that they can work on natural images. So this also aligns with my understanding. So this is computer vision. It's supposed to recognize or understand the natural image other than synthetic image most of the time. Yeah. The conclusion is that by Tolly et al. Is that ImageNet model drops well below the expectation set by the image validation set. Yeah, this is common sense, right? And then the author, the Tolly made a claim or argument that robustness technique should aim to improve both effective robustness and relative robustness. Yeah. The effective robustness here, it meant improvements in accuracy and the distribution shift. Going from one data set to another one, you should still be able to not suffer too much from the accuracy. Okay. And the relative robustness, it captures any improvement in out of distribution accuracy. Okay. Improvements. So the difference is that yeah, there's some difference. So the effective robustness means that there's some relationship out there. Relative, I don't think there's a relationship. Okay. After Tolly defined the effective and the relative robustness, so the author start to study the robustness of their proposed model. Again, this is the data set that is related to ImageNet. These are more generalized data set. You can see that this is after transfer learning or zero-shot transfer, okay? And this is the original ImageNet score. And you can see that, how do you say that? See, for example, you take this for example, okay? So on the original ImageNet, of course, this is also zero-shot for clip model. Okay, they got 77%, but suppose you doing some transfer learning. I think by this time they do have some training data. This is why the number will go up, but they do not explicitly mention this by the authors. They got to 81% or 82%. So you can see they get higher. And you can see that, let me use this. You see, suppose you use a VIT clip. And this is the efficient at noisy student. And you can see that definitely you can see the model is more robust. The clip model is more robust because it improved the classification accuracy after the transfer learning. Make sense? And also, you can see this is also the case. This is efficient net, right? And you can see that the efficient net would suffer very much from the accuracy if the evaluation set is very much different than the image net. You see, this is almost how do you say that? This is several data sets, okay? Most of them, they are fairly good. Oh, I mean, after the transfer, it suffered more. You see, but this one, it suffered like this, right? Suffered. But for this ones, it suffered this much, right? It lost that much. Okay. You got this? Okay. So that means either your transfer set is closer to ImageNet or distant from ImageNet. You can see the suffer or improvement of the proposed VIT model or clip VIT is more robust to task shift. Okay. Then they do some figure 14. What does the figure 13 talk about? Yeah, this is easy to understand. Let me zoom in a little bit first so you can see that more clearly. Oops. Yeah, this one. So they say, I think this is similar to the figure 12, but in this way, they run some average on different data sets, okay? Average on all the natural distributions. So you remember they say they transferred or there's some variation data set of the ImageNet mentioned by Tolly et al. There's 7 natural distribution shifts. And this is the ideal line, right? So after the shifting the task or shifting the domain, this is y equals to x, okay, ideal case. And you can see that with ZeroShot Clip, this is a job, okay? This is a job. But if you're using the standard ImageNet training or existing robustness techniques, the job is very much too much. So this is why the ZeroShot Clip is very much more robust. But I don't think it's It's more robust than other techniques, but I don't think it's very robust because you can see it still dropped a lot when you shift when the natural distribution shifted. Okay, then we move on to figure 14. Okay, figure 14. I think figure 14 contains a lot of message. First of all, we just focusing on the baseline. Baseline is ImageNet ZeroShot Clip. Okay, I want to make this bigger. This is the baseline, and it's the orange line here. Yeah, using the yellow, you won't be able to see. And the meaning of adapt, I think for speech people, everyone knows what the adaptation means. It means supervised fine-tuning for machine learning people, okay, using the full data set. So this is why we can change it. No, sorry, I don't have another pen. So adapt to class shift, and that means all you have to do is for each class. What do you mean? You may ask, what does the class shift mean? I think it was because, remember the 7 distribution things here? I think the author meant something like this. So the target class across 7 transfer datasets are not always perfectly aligned with those of ImageNet. For example, so the person class in YouTube BB, but ImageNet, the classes could be baseball player, bridge groom, scuba diver. Those are all person, okay? But then you may need a pooling methods to pull these classes into this one. Person classes, okay. Person class. This, I think this means adapt to class shift, okay? But what does the adapt to ImageNet mean? I think this is fairly straightforward. Basically just a fine-tune on ImageNet. Fine-tune your linear classifier on ImageNet. And you can see that the author meant that it's smaller. They got a very good result. You see, increased its ImageNet accuracy by 9.2%. And it tied the accuracy of the 2018 SORTA. Very, very, very good result, I would say. But they do ask this question. So it's surprising to see this increase. But this improvement failed to translate into any improvement in average performance under distribution shift. What does that mean? So the authors didn't contend with just improve the accuracy for ImageNet alone, because they want to see the improvement on other data set, for example, 7 other data set which has the natural distribution shift. And you can see that actually, after you do the adaptation, you can see that for the other data sets, the performance actually dropped. You see? You got this? And this is a class sampled image net. And this is a distribution. You can see when you adapt to a class shift, definitely common sense is making the model better. But after you adapt to the ImageNet data, you can see your performance actually dropped. Why is that? So they also had a lot of assumptions. One thing they talk about is why this is a little or no increase in accuracy under distribution shift. But they cannot get a confident answer to this. I'm sure they couldn't, because this is the work they have done couldn't answer these questions too. This is also why it's interesting. They say they try to encourage the authors of other paper to study these questions on their models as well. It might be future work of this paper, okay. But I think it's common sense, although we don't know the reason, okay. The distribution are different. You fine tune on certain distribution, it won't work on other distribution. I can understand this, but why or what exactly the mechanism is so this failed, I really don't know. Neither the author be able to explain. Okay, then I think I finished explaining the figure 14. Still, this one, it shows that also you see this one, you adapt to ImageNet. So it's interesting that the ImageNet v2 also got improved, but for the other ones, for the other data set with the natural distribution shift, it went down. The performance went down. The interesting they talk about is that I'm not a computer vision researcher, but according to the author, ImageNet v2 follows the way that the ImageNet organized their data. Does that mean the distribution of the ImageNet v2 is similar to the ImageNet? But maybe other data sets, although they have the name of, they start from ImageNet, but their distribution is way different than the original ImageNet. Okay. And also you can see that adapt to class shift. This one is fairly useful because I think the pooling thing works very well. So the YouTube BB dataset can get way higher results. Okay. And also, one thing they're trying to say is, let's move on to figure 15. Okay. We're almost there, okay? Almost done. So this is the ideal case, x equal to y. And they're saying that they're studying that for clip model, they play that with the few shot learning, which means they can have one sample, two sample, four sample, or all the training set to learn the linear classifier. Okay. And of course, you can see that the accuracy went up, right? After having more data. And this is a few shot learning. Let me use this. This is a few shot learning. This is a few shot learning. I'm sorry. Yes, this is few shot learning. And look at this. You may not be able to see this. This is the zero shot learning. Okay. And you may say, okay, why I have all the shots and this is still worse? I asked the question too. It seems that when you have all the shots there, it's still not getting better than the zero shot. So this is the conclusion here. It increased effective robustness compared to existing ImageNet model, but less robust than ZeroShot Clip. But the reason was because when they're using all the samples to train or fine-tune the linear classifier on top of the clip model, they only use the ImageNet. They only use the ImageNet data. Okay. But remember this. This is a 7 natural distribution set. So it's not, so you still have the natural distribution shift. So you still have the mismatch thing. So in this case, zero shot learning on average is better than doing the few shots learning. Make sense? Okay. And they also say that and also they compare that with robustness intervention. In this one, you see the difference is huge. So you can see that this is why they're saying this is a more even the few shots learning is not as good as the zero shot learning, but you can see that eventually, first of all, eventually, you see, it's gonna be exceeding the performance of zero shot when you have more and more data, or having more data that are representing the natural distribution shift. You're gonna be getting getting there, right? And you can see the gap between the blue, the orange line versus the, what do you call that, brown line, brown dots, a huge gap there. Okay, although you may see that finally you see that the gap is getting smaller and smaller, but this means that the effective robustness, so it means that you have few shots, you can get way better results than doing the traditional robustness based method. Okay. And this is yeah, finally they talk about, yeah, this is the conclusion here of figure 15. So high effective robustness seem to result from minimizing the amount of distribution specific training data a model has access to, but it comes at a cost of reducing data-specific performance. That means, well, I think this generally lies my understanding with the super large model. So they do not train their model on a specific data set, but instead they are trying to leverage data with coming from as many distributions as possible. So eventually, when they have to use the zero-shot transfer learning, because the representation has the capability of generalization, so they won't be suffering from the original specific data set distribution, or they won't be limited to the or certain specific data set distribution. Okay, what are they trying? What did these super large model learn? So I don't think I can cover it in this video, but I will try to do this in the following videos. Try to share with you about my understanding of these super large language model or pre-trained model, why this works, on how this works. Okay. Yeah, finally to talk about the similar findings in the NLP domain. Yeah, they call the Hendricks. Hendricks also reported that pre-training improved the relative robustness on sentiment analysis. Yeah. Also, yeah, of course, little evidence of effective robustness improvement to date. All right. I finished the section 3, experimental analysis. Hope you get some understanding or better understanding of the clip paper. And I will be finish the rest of part of the sections, which could be section 4 to section 5, section 6. Eventually, I think section 7, section 8, and section 9, conclusion. So we have a 5 section to go in the next video, but I think I can finish in the next video. And thank you for watching our video. We're Olewave channel. This is the last day of 2022. I wish everybody Happy New Year, and please stay tuned.